Everyone, I'm Jaideep Saha from the National University of Singapore, and I'm going to present our paper titled Comparative Overview of Power Balance Control for Two-Stage and Single-Stage Isolated MVAC-LVDC Cascaded Converters. So coming to the outline, first I'll give a brief introduction about the importance of MVAC-LVDC conversion, the MVAC-LVDC conversion strategies, which have two major ones, then the power outage imbalance issue in such converters, the power balance control schemes, experimental verification, and conclusion. So, as it is quite well known, line frequency transformer based solutions have dominated the interfacing of microgrids with the utility grid. Now, due to the present requirement of AC-DC conversion when it comes to interfacing of microgrids, there are additional power electronic reinforcements like the back-to-back converters as shown here. But there are emerging solutions of medium frequency transfer based medium voltage AC low voltage DC conversions, which are being quite well studied, and it is shown that in terms of volume, weight, and losses, this new conversion architecture, which is based on medium frequency transformers, is much better than the line frequency transformer based solutions with power electronic reinforcement. And not to forget, in terms of cost, they are quite comparable. So the MVAC-LVDC conversion solution is quite competitive. Now here is a schematic of the grid interfacing MVAC-LVDC conversion, where one of the submodules is shown here. So it's in an input series output parallel configuration. Now delving deeper into the conversion strategies. So there are two major types of conversion strategies. First one is the two-stage cascaded modular SST type of conversion strategy, where you have a rectification stage in the front end and then a DC-DC dual active bridge type of stage in the second stage. So as you can understand, there is a AC-DC and then an isolated DC-DC conversion, whereas for the single stage counterpart, there is a single stage AC-DC conversion. So there is a front-end matrix converter which converts AC to high frequency AC directly, and then this high frequency AC is converted to DC. And of course, these are going to be bidirectional. So usually due to two stages in the two-stage type of conversion, the losses are more, and it is expected to have lower efficiency. Now, let us look at the power routing imbalance issue. First, in the case of the two-stage conversion strategy. So here in equation 1, the power transfer equation is given for a submodule I. So as can be observed, in the denominator, there is a term of the interbridge inductance of the DC-DC DAB. So there is an unavoidable issue of an error in this LS, because these inductors are never perfectly matched with the intended value. So there will be some errors and there will be some differences introduced in one submodule with respect to the other. So if such an error, let's say, as shown here, occurs, then what happens is it causes a difference in the power transfer through a submodule, as can be seen here. So a Taylor series expansion is shown here, and which shows that whenever there is an error, there will be a difference in the power transfer. So how is this manifested? So if, let's say, the inductor has a positive error, that it is slightly has a higher value than what is intended, so it leads to this current ID over here to be lower. Why? Because the power transfer is lower due to a higher inductance, as can be seen here. So once this is lower, the VHF, this actually rises. So there can be a derivation which shows that let's say if LS, if this is higher, then this is lower, and then this is higher. So then this way the DC link voltages of the submodules would get imbalanced, and it would get manifested in the front end pole voltage because the rectifier modulation indexes are kept constant. So the pole voltage would have higher harmonics or something which is not intended. Similarly, in the case of the single stage conversion strategy, here also, if there is an error, then there will be a imbalance in the power transfer between the submodules, as can be seen through equation 3 here. And then there will be a manifestation in terms of imbalance in the grid side submodules voltage, as shown here. So if the error is higher, then that particular submodule would show a higher voltage in the front end side. So this would again lead to increment in harmonics in the pole voltage as well as the grid current. Now there are some mitigation techniques. So for the two-stage conversion, there are two controls which are needed. First is the first stage rectifier control, and then there is the second stage control. So if we try to mitigate this power imbalance, the first strategy used could be for the first stage, where you try to match the voltages of the DC link. But for that, you have to use different modulation indices for the different active front-end rectifiers. So then it would lead to a higher harmonic content, which is unintended. So what is instead done, and it is already proposed in the literature, that there are some correction terms which are introduced. So you can see even here. So these correction terms for the phase shifts actually counteract these errors in the leakage inductor. And then it would mitigate the power imbalance issue, and then it would try to equalize all these DC link voltages, and the current harmonics would be only dominantly seen according at 2n FSW, or 2 into n into just switching frequency of the front end rectifier. So then it can be quite easily eliminated by using a simple filter, and lower order harmonics are expected to be eliminated. Now, for the single stage conversion type, there is a similar strategy which is used. So it is not well studied in the literature, but when we try to use the similar strategy, then we have to introduce this phase shift correction terms in the from the power balance controller in the LVDC bus voltage control. So in this case, there will be just a single stage control because it's a single stage converter. So when we introduce this, then basically it would again counteract the imbalance in power, and it would also counteract the imbalance in voltages and try to equalize them. And the dominant harmonic evaluation is quite straightforward, because from each submodule there will be dominant harmonics centered around double the switching frequency, and they'll just get added up in the grid current. And so the grid current's dominant harmonic would be centered around twice the switching frequency. Now, coming to the experimental verification section, we have done a rigorous study. On the left is the single stage CMBDAB, MBDAB prototype, and on the right is the two-stage CMSST prototype, which is the more conventional one. So just to mention a point over here, usually the mismatches in inductor is usually in the range of 5 to 8% as observed in the industry. But for our experimental verification and studies, we have considered a 20% mismatch scenario so that we can test these controllers in a worst case scenario. So that is why it is mentioned that there's a 20% mismatch in case of the leakage inductors or the interbridge inductors in case of CMSST single two-stage one, as well as the single stage CMVDAB one as well. Okay, let's proceed. And these are the experimental verification results for the two-stage CMSST. So at 100% load with 20% mismatch. So before the power balance controller is activated, we can see that there is a mismatch in the DC link voltages due to the mismatch in power. But due to similar phase shift utilized, the DAB current is fairly equal. But then when we use the correction terms, then the DAB current actually gets a little bit shifted away from each other. But because we are trying to manage the equalizing of power transfer, so the DC link voltages actually equalize, and unlike in the previous case before activation where the THD is quite high, we can now get a very good THD which is at 3.5%. So let's proceed and look at the experimental results of the single stage CMVDAB prototype. Here it's also this similar thing which is happening, and before the activation of PBCs, we can see there is a imbalance in the power causing an imbalance in the grid side submodule AC voltages, which is leading to a high THD in the grid side current, which is unwarranted. And then when the PBC is activated, then at steady state we can see that there is no imbalance either in the power or voltage, and the current has become quite nice in terms of quality, and the THD is quite low. So let us also look into the experimentally obtained harmonic spectrum. So the red one shows before the power balance controller is activated, and the green one shows after. So on the left is for the 100% load scenario, and on the right side is for the 50% load scenario. So here it can be seen that the dominant harmonics are at 6 FSW, which is 2N FSW, because in our experimentation we have taken only 3 submodules for simplicity of explanation. And once the PBC is activated, all these harmonics are attenuated. So the similar kind of a trend can be seen in 50% load. But one important thing to note is that we can see for this two-stage CMSST, there is still some lower order harmonics which are residual. So this is because even if we try to keep the modulation index of the front end rectifier for all the submodules equal, but practically it can't be kept exactly equal. So these lower order harmonics are possibly going to stay. Whereas when we look at the experimentally obtained harmonic spectrum for the single stage conversion prototype, here at 100% load or 50% load, we can see the dominant harmonics at twice the switching frequency, and they get attenuated when the power balance controller is activated in case 2, that is the green one. So here basically, because there is a single peak in terms of the switching frequencies harmonic spectrum, so once the power balance controller is successful in eliminating that, then most of the major harmonics can be eliminated, and there are no lower order harmonics remaining. So there, I think you would also see a peak near the lower order thing, which might cause a doubt in your mind, but that is the resonant frequency of the half bridge submodules, capacitor, and the filter inductor. So that is a resonance of filter effect. which is also a very low magnitude. So that is and not a major issue, and we can see the THDs are dropping to below 2.5%. So coming to the conclusion, the unavoidable issue of power routing imbalance has been explored in this paper, which is majorly due to the parameter mismatch effect, which is outlined for both the single stage and two stage topologies. The power balance control scheme and its augmentation to the LVDC bus control is discussed for both the converter topologies. An explanation is also given regarding the utilized experimental prototypes, and suitable results are presented to show the operation during the PBC activation event for both the topologies. And the PBC scheme is found to be quite effective in mitigating the power imbalance issue for both the topologies, and it in turn ensures very good grid-side power quality. Two-stage CMSST topology basically exhibits a higher grid current THD compared to the single stage counterpart, because the front end rectifiers, residual lower order switching harmonics still remain. And just for curiosity of the listeners, I would like to mention that the experimental efficiencies obtained for the two-stage topology is slightly lower, around 93% compared to the single stage one, which is 95%, which is quite according to the expected characteristics. So thank you, and we'll be very happy to answer your questions.